This is our afternoon breakout session titled, Is Your Transmitter Really Ready for ATSC 3.0, which is presented by Perry Priestley, Chief Operating Officer for Broadcast Electronics. I've known Perry for a long time. He's worked in the professional broadcast industry for over 45 years. He joined Broadcast Electronics as COO in June of this year. Previously, he held the position of Chief Executive Officer at Anywave Communication Technologies, a wholly owned subsidiary of Suzhou, China? Whatever.
You can never pronounce it.
Nobody will know. He has also held positions in sales and business development with Linear Industries Brazil, Ubiquity Digital Corporation, now Xperi, Thales, now Thomson Broadcast, and EEV Marconi, and Philips Pi TV in the UK. Perry's been the lead commercial coordinator in notable projects over the world and has been a significant contributor to many new product releases in the radio and television broadcast market. Pleased to have Perry here today to discuss the technologies available to implement ATSC 3.0. Please welcome Perry Priestley.
Gary, thank you very much. Appreciate that. As Gary mentioned, I've known him for quite a few years and missed in the industry now. So, thank you for a great introduction. Thank you for all coming. I'd like to, it's a relatively small group, so I'd like to keep this relatively informal. If you have a question, just put your hand up as I'm talking and we can address it. Because if you're like me, I can think of something, of a question, and 5 minutes later I'll have forgotten it. So rather than wait till the end of the presentation. So as I said, any questions, just we'll jump right into it. So I'm going to talk today not just about transmitters, although that will be the emphasis of the actual program. I'm actually going to talk initially about why are we moving to ATSC 3, what's the point, what are the options, what will change. I'll give a brief technical summary on ATSC 3, and then I'll focus on the differences between ATSC 1 and ATSC 3, in particular towards the transmitter and transmission equipment. I'll give a very brief summary at the end and then be open again for further questions. My gadget is over there. Sorry. Okay. So there's been a recent, very interesting article that I read just a week or so ago about the future of television, the future of content, the future of video, how we will receive content. And I thought, I took this idea and, did I jump to that? There we go. I took this concept and looked at it and looked at the 4 potential options of what will be television, what will be our delivery services in the year 2030, in 10 years' time. And it came down to 4 results. There's 4 possible outcomes of what will happen to our industry. The first one is that there'll be hundreds of options, too many options, lots of confusion, total chaos. Television will be mixed in with every other type of service, and it will get a thinner and thinner slice of the pie, and we will actually not really exist, but still, get by on the meager, small part of the pie that we can get. The second option is even worse. It's what's called the universal superstore. It means that digital platform companies, global platform companies as we know them today, will actually take over from national broadcasters, they'll take over from local broadcasters, and pretty much television over the air will disappear. The third option is pretty much the same, but instead it'll be run by the content. Content is king, as we all know, and the content providers will dominate the market. They will monopolize the market using content as the actual main collateral. They will use the global platforms to deliver it, and again, over-the-air television and radio will be a thing of the past and obsolete. And the fourth option, and this was truly determined by a fairly well established company, was that television can survive. Over-the-air television can actually make a difference. ATSC 3 can be implemented and it will make a transformation and it will keep TV present and relevant. And if it comes to those four options, I don't know what yours is, but my vote is number 4, if there is a choice here. So everybody's comparing ATSC 1 and 3. When we move from NTSC to ATSC 1, everybody's comparing ATSC 1 to ATSC 3, and it's not the same. It's really very different. When we moved to ATSC 1, nothing really changed. It did not generate any more revenue. Okay, we're able to deliver HD. It took 10 years or so before a lot of stations, even the major networks, added a second or a third channel, which generated relatively meager results. So ATSC 1 was forced upon us. It was probably a good idea at the time, but it really didn't affect the way people viewed TV, and it didn't affect the revenue sources of television stations. ATSC 3 is completely different. It will revolutionize, and that's not an overstatement. It will revolutionize this industry. It will change it completely from what it is today. It's the same effect of wireless and the internet on the plain old telephone service. Every person in every department, in every TV station, and every viewer will have their habits change, their work will change. So it's a big deal. Why? Why is it a big deal? Well, why are we actually thinking about this? Well, things, like tablets are completely widespread these days. Mobile devices, 20 years ago, who would think everybody would have a mobile phone, from an 85-year-old grandmother to a 8-year-old boy these days has a mobile phone. Some people have 2 mobile phones. Some people have 3 mobile phones. I always think it depends on how many mistresses you have. It depends on how many phones you have. There's a need for higher resolution, 4K, 8K, etc. As we know, spectrum is becoming increasingly sparse. We're all very familiar with the repack. Interactivity is becoming an issue. Everybody demands it. Everybody expects it. There's been significant major improvements in compression, and if we don't change the standard, we can't utilize those compression techniques. We're still using MPEG-2, which was invented in 1978. I don't know if any of you would keep a car that long, but it's just, you just don't try to use a technology it's that old. And of course, better audience measurement is needed and expected to make revenue these days. Everybody wants to know not who's just watching, but where they're watching, how often they watch, when do they change channel, when do they move around the living room. That's the information that will be available with ATSC 3. You'll know exactly who, where, and what is watching. ATSC 3 will bring all kinds of new, wonderful revenue-generating opportunities, from targeted advertising and targeted content. That means in the any city. On the west side, you could have one program. On the east side, you could have another. You can focus on mobile television to the north of the city, on where the highway is, and you can do ultra-high definition to the south of the city. You can change the content. You can change the actual method of reception. There'll be subscription system services, and then, of course, because of the actual bandwidth efficiency, there'll be a lot more opportunity to do more channels at a higher quality. There'll be mobile services, the first time television has ever been able to address a mobile market. Even NTSC didn't work in a car, and you couldn't get a receiver in the car. So that didn't work. ATSC has never worked in a mobile environment. ATSC 3 can and will be in trains, boats, and planes. Hopefully in the back of cars, not the front of cars, but you never know. It's got a greater capacity due to the actual efficiency of the system, and so we'll be able to do lots of other kinds of things, potentially being like an edge network, providing data services. One of the things I think will be cool is it can do a second screen. That means you can send like the main HD will be football, on a second screen, the same sort of data in the same stream over the same air. You will actually have supportive data, maybe that you can watch on your phone. So it'll have all the stats. Maybe it'll have the red zone of another game on at the same time, all through the same signal. And of course, all of this because of the IP return through your cell phone or through other internet internet connectivity, you'll have two-way system. So TV station will be able to measure not only who's watching, where they're watching, how often they're watching it, but the complete measurement. So some technical stuff. As I said, any questions, don't be shy. Ultra-high definition is an opportunity with ATSC 3, something that's called high dynamic range and a wide color gamut, and I'll explain that in a minute, is now going to be available at, as I said, a better compression system, up to 4 times more efficient. It actually, depending on the technology you use, it can be up to 16 times. You can get 16 the amount of programs, or 16 times the quality you actually have today. Frame rates of up to 120 frames per second is available. It's super high quality, like a Blu-ray is actually only 24 frames per second, as an example. And all kinds of types of audio, from 5.1 all the way up to 7.12. On the left-hand side of the screen, you'll see the color spectrum, green, red, blue. That's every color that does exist. And that is what your eye can see. That's somebody with good eyes, by the way, not my eye. But if somebody can see those kind of colors, that's the human eye. And that is what high definition covers today. So we cover a fairly large percentage of what the human eye can see, but there's still, oh my gosh, sorry. Talk about bad timing here. I apologize, switch that off. So that's what high definition, what we see today, covers it. When we move to ultra high definition, that's what covers it. It goes beyond the human eye, equivalent to about 4K. So when people ask you if you should really go to 8K, my opinion is no, because there's not much left to see. It's a perception, it's a depth thing, but in terms of colors, that 4K ultra high definition covers everything. The biggest thing about ATSC 3, in my opinion, is that it's OFDM. OFDM is, compared to ATSC 1, it's a multi-carrier system, where ATSC 1 was a single carrier system. Now, who else uses OFDM? Well, everybody. There isn't a single communication systems in the world that doesn't use OFDM. Every digital radio, DAB, DRM, HD radio, uses OFDM. Every Wi-Fi standard, every digital TV standard in the world, DVB-T2, ISDB-T, all use OFDM. The only one standard that doesn't use OFDM is ATSC. Still don't know why we chose that standard. However, we are moving away from it. ATSC 1 isn't very good at selective fading immunity. It's not very good at getting resilience to interference. It's not very spectral efficient, and it actually has a lot of linear distortion, or opposite to equalization, which is often found in combiners and filters and things. ATSC 3 has all of those as tremendous features. But the biggest thing that OFDM provides is mobility and portability. So a quick comparison, ATSC is a single carrier. It's a fixed bit rate. You've got a 15 dBs carrier to noise ratio. If you're 16 dBs, you're in good shape. If you're 14, you're off the air. It's fixed. It supports HD as well as SD. But broadband and broadcast are completely different customers, different people in a different area. ATSC 3, however, has flexible bits rates, multiple opportunities to deliver all kinds of technology, whether using different PLPs. It allows for ultra-high definition as well as HD, and it has bit rates from as low as 4 megabits per second all the way up to 64 megabits per second. The typical will be around 36, potentially as low as 22, depending on which market you target. As I said, it supports 4K. And the big thing here as well, you can join broadband and broadcast together because they use the same internet protocol technology. So let's do some comparisons between ATSC 3 and ATSC 1. The first thing from an engineering point of view is that ATSC 1 typically is just an 8 VSB signal. So you measure the single system. The only thing you really measure is the 8 levels. Here you see the constellation. From this, you can measure signal to noise. You can determine phase errors. You can determine things, but that's it. When you talk about ATSC3, there's literally dozens and dozens of actual measurements you can make, everything from 4 QPSK to 64 QAM, 128 QAM, and so forth. There's lots and lots, hundreds, if not thousands of options on 8 VSB, on ATSC3. PLP will be a name that every engineer will need to know backwards and forwards and upside down. PLPs will become everybody's and every engineer's main focus in life. A PLP determines how somebody watches, where they watch, what they watch on. And you can vary that. That's one thing about ATSC3. It is literally thousands of adjustments. So you can adjust the type of bit rate, you can adjust the type of forward error correction, and another 50 other things in terms of type of modulation from QAM and QPSK, etc. The more the robust the signal, the higher the carrier to noise, but the lower the bit rate. So you can choose to target maybe small devices with a very high forward error correction, so you can focus on laptops, cell phones, or you can go with a very high bit rate but a low carrier to noise ratio, and that would be ultra high definition for the living room. So it basically looks like this on a map. If you go for low bit rate, high forward error correction, you're going to get a much wider territory, smaller with the standard definition, and much smaller with ultra high definition. But you can choose that. You can choose that you can vary that from the time of the day. Mornings you could focus on travel time and focus on people in vehicles. In the afternoon you could focus on ultra high definition and sitcoms, and in the evening multiple channels. So all kinds of variables that you can do on the fly with ATSC3. So moving on through, which now we're going to lean towards transmitters, as that was in the title of the presentation, so I will get to that. The differences between ATSC and ATSC3, and the main thing about a TV transmitter is what's called the peak to average ratio, the PAR, or the PARP. In ATSC1, it's 6 dBs. In ATSC3, it's 8 and a little bit more, 8 dBs or more. So that doesn't sound like that much, 2 dBs, but 2 dBs, don't forget 3 dBs is twice the power. So 2 dBs is a lot more power, and there's a lot more instantaneous power. This instantaneous power, this instantaneous peak only happens for a very, very small period of time, but your amplifier needs to actually withstand that. And if it doesn't, it can do one of two things. It can, if it's organized badly, break, or it can just distort so much that you actually lose a lot of the actual carrier to noise ratio. So yesterday's transmitter, an old transmitter, may not survive the additional power. It's like if you have a 10 kilowatt transmitter, realistically, if it's not designed to run 16 to 18 kilowatts, it really won't do ATSC3. It does mean that you can run ATSC3, but instead of running an equivalent power of 10 kilowatts, you'll be running an equivalent power of 6 kilowatts. So what you need to do, if you own a transmitter that's not in the repack, that you haven't bought a brand new transmitter and you haven't bought the latest transmitter, you need to know where its compression point is. And you can do that with various basic ATSC1 test equipment. And if you have significant compression, you really should be looking at a new transmitter. If you have mild compression, there might be ways of overcoming it with an exciter. And if you have a lot of compression, then you really need to be looking at a new transmitter. What is peak to average ratio? It's when all the carriers at one instantaneous time overlap. It's basically the symbols are completely varying all the time, and if they appear at the same time in the same carriers, the powers all add up, and then you get a lot higher power. So there is actually a technology inside ATSC3 that tries to reduce the peak to average power. It's a peak to average power reduction program, and that tries to actually overcome this problem. If the higher the peak to average ratio, the higher your amplifier capability needs to be. But unfortunately, it's not running at that high power level all the time. It's actually running at the average power. So the efficiency significantly drops off. In other words, the cost of running the transmitter is going to be a lot higher. And it could be and if you're using the wrong technology, it's a big difference. Typically, we've seen on an older transmitter between a 10 and a 12% difference in consumption. So to get the same kind of power output as you are with ATSC, you're going to actually run 10 to 12% higher in electricity bills. So there's a technology called ACE, and that basically just grabs hold of the symbols and reorganizes them in a random way on, it's called, as I said, it's called ACE. It allows the peak to average ratio not to be so high. It reduces it. We've done a lot of measurements and worked on this, and it's unfortunately not as good as the people who invented it said it is. They're saying anywhere up to 4 dB improvement in power, but you can see some charts here. We did some measurements, and we only got about half a dB back improvement. So at best case, you're still going to be 1.5 to 2 dB still difference between ATSC 1 and ATSC 3. If you're buying a brand new transmitter today, which a lot of people are doing, it's most likely, and I will get to that slide in a minute, most likely going to have a latest technology transistor, and you're most likely going to be okay. But there's still things to look out for, and I would like to cover those as well. But a lot of people then say, well, okay, my transmitter's old, but really what power do I need? You know, I've got a 20 kilowatt today, do I still need 20 kilowatts? Well, it depends. It really does. It depends on whether you want to replicate your service. Because don't forget, now you can change, without changing your antenna, without changing anything, you can change the type of coverage on the fly. You can change it to mobile coverage. You can change it to high definition. You can actually redirect it. And you can have different coverages in different areas. So it's a different game. It's not apples to apples, ATSC 183 to ATSC 1 coverage. It really depends on what you're planning to do as a business. Are you aiming for indoor reception? Are you aiming for 4K in the living room? And that's it. And that's a different business. That means you'll need, people need to have antennas on the roofs, and you'll need as much power as you can get. Or are you focusing on people sitting in buses or in cars or trains and looking at our small devices? The whole concept of television is going to change, so we have to think in a different way. And don't forget, the main thing is the robustness versus the payload. The more robust the signal, the smaller the payload. The higher the payload, the less robustness it is. And, you know, what type of service is, and you can, these, as I said, can be all adjusted with what's called PLPs and LDM. And the current thinking, of course, by the FCC have said you should have the same power as you have today with ATSC 1. So if your ERP won't change, your TPO won't change, they're just letting you go. But you can reduce that because, again, they can't measure it like they used to measure it before. So let's talk quickly about measurements. What do you measure on an ATSC 3 system? Well, pretty much the same as ATSC 1 when it comes to it. It's typically referred to in ATSC 3 as modulation error ratio, MER. In ATSC 1, it was related to SNR, signal to noise ratio. They really mean the same thing. There's a slightly different measurement. One thing of importance is that the shoulder measurements, as we measure the shoulders on the actual signal, they will be referred to and referenced to the carrier now, the center of the actual frequency band, whereas it used to be referenced to the pilot. If you always remembered, you'd measure 47 dBs with the shoulders. That's the minimum the FCC recommended. Well, there is no pilot anymore, so you have to measure it to the carrier. So you can actually deduct 10 dBs off your signal. So if you were measuring 47, then ideally 37 is that's a good number. Obviously, the higher the better. I would prefer to see 40 to 50 dB shoulders. And the same with signal to noise and MER should be about the same. Ideally, aim for something like between 32 and 35 dBs. The system is not as dependent on linear distortion. Once upon a time, we used to have linear and nonlinear correction in the exciter. The linear distortion is usually generated by the filters and combiners and anything that has a phase change. That linear distortion was corrected for partially inside the receiver via an equalizer. That is not necessary anymore because OFDM doesn't actually worry about linear distortion. And I'll explain briefly why later. So what else is going to change in the transmitter? Well, the most dramatic thing in your transmitter will be the exciter. If you don't have an ATSC3 exciter, then you don't go ATSC3. Be careful about people telling you that their exciter is ATSC3 compatible. It's very different to actually really working with ATSC3. And there are technologies that are already being implemented and still being put into the standard that haven't been finalized yet. And so having that as part of your exciter is critical. It's relatively easy to swap out an exciter. Probably most of you have done this. So it's just a matter of making sure it fits. You can take your old ATSC1 exciter out, put a new ATSC3 exciter in, just make sure it fits in terms of mechanical cooling, the levels, the feedback, the samples. It's very easy to do. Filters. As I mentioned before, the linear distortion is not so important as in ATSC3 as it is ATSC1. There's a slightly different bandwidth in ATSC3, but you can actually overcome that bandwidth by, you can literally reduce the size of the band in ATSC3. If you want to, you can get rid of carriers. If you get rid of the carriers, of course, you reduce the actual amount of bits. The shoulder performance in ATSC1 relied a lot on the performance of the filter. That's not going to be true in ATSC3. Most of the correction in the exciter will compensate for the shoulders and so forth. 8-pole filters, they're typically tighter because they were maybe on channel 14 or they had an adjacent channel that there was some sensitivity to, so they're going to be tighter. Those should be checked. If you've got an 8-pole filter that was tightly tuned, that you had on an old IoT, or as I said, an adjacent channel issue, then they should be looked at because they're probably too narrowly tuned. As I mentioned, the big advantage of OFDM is it's not sensitive to group delay. The carriers are too small, so the group delay changes over a very, very small bandwidth are insignificant. So there's no equalization errors, there's no what's called linear distortion, so that's a good thing. You don't have to worry about that as much as we did with ATSC1. If you haven't purchased a filter yet, I would recommend, I don't sell filters, so this is not a sales pitch. I would recommend what's called a dual coupled or dual cross system. It's, as you can probably just tell here you can see there's a significant improvement for the same kind of filter. You can see actually a drop in signal strength there. So it's got better insertion loss. It's certainly a lot more selective, and so you can get a better isolation from adjacent channels. It's ideal for ATSC3. So again, dual cross filters. Moving back to transmitters and thinking, well, I'm not in the repack. I've still got an IoT transmitter. Will it work? Most likely it will. You may have to reduce the power. Cathode emission in IoTs are obviously critical. As the tube gets older, it has less emission. It starts to compress earlier. In ATSC1, you wouldn't notice it as quickly. In ATSC3, you'll notice it a lot quicker. So you'll notice a tube dying quicker in ATSC3 because of the actual peak to average ratio changes. So it's something to look at. You may need to be replacing tubes more often or looking at replacing the transmitter itself. There's also a significant reduction in efficiency, and it's more notable in IoTs and older IoTs than it is newer IoTs. Old solid-state transmitters, Class A or AB, most likely AB type of transmitters, are going to have a problem with the ATSC 3 in particular, again, back to the peak to average ratio, they're going to be, first of all, they're going to be really, really inefficient. I would say anything down to 15% efficiency is going to be seen in an old transmitter, and you just shouldn't be operating a transmitter that low. It's just throwing money away. Typical new modern solid-state transmitters look at efficiencies in the region of 50%. And that's a big difference, especially if you're running anything above about 3 or 4 kilowatts. It really, you'd pay for a new transmitter probably within a year if you're running a really old solid state. I know it's a lot of outlay, but it makes a big difference in terms of finances. There's a technology called Doherty modulation. Doherty modulation is actually not a new technology. It came out in 1938, actually. It was used originally on continental radio transmitters. But it's currently used. It's very, very good with high peak to average ratio type technologies. It's ideal for ATSC 3. The versions start with BLF. They're all made by one company. And the version that's most commonly used right now, I think, is the 888E or D. There are a lot of 888B transmitters out there that are labeled as ATSC 3 ready, but that's not going to work very well because, again, the peak to average ratio, and if you can see here, even between the symmetrical and non-symmetrical, we've got a 6 dB ratio here, and that's perfect for ATSC 1. Because that's what ATSC 1 is, 6 dBs. ATSC 3, however, is 8 dBs. And as you can see, we're dropping off quite significantly here. So you'll see with even new transmitters within the last few years that have used a BLF 888B are going to see a really large difference in efficiency when you move to ATSC 3. So something to look out for. The difference between symmetrical and asymmetric is between the E, anything from D onwards. So B, D are all versions, B and D are all the symmetric, and the E is the asymmetrical. There's a new transistor coming out, the 989. So if you can wait, it would be a good thing to do because there's a 989 which is significantly more efficient and has even better drop-off than the actual E version. It also has a capability of 250 watts instead of 150 and provides similar efficiencies, even slightly higher. Yes, sir?
They're both 50-volt transistors.
They're all, yeah, A, B, there's no C. A, B, D, E are all 50 volts, correct.
Okay, so what's the difference? The gain in the transistor is different?
No, it's C. Oops. The difference between symmetric and asymmetric is Doherty is made of 2 transistors. And if they're identical, they're symmetric. And if one is working slightly different and organized in a different way, it's an asymmetric design. So the combining of them is combining a high impedance with a low impedance transistor. So yeah, they're designed in a slightly different way. Yeah, so you're right. They're both 50 volts, and they both work on what's called the Doherty technique, which the Doherty technique means one transistor looks after the peaks and the other transistor looks after the average power. And that's why it's so good for ATSC 3 and OFDM type technology.
So we're still paying the Doherty estate.
I think Joseph Doherty is not getting any royalties from that. I think he actually sold them to Continental Electronics, and I think that patent ran out long time ago.
So you want asymmetric?
You definitely want asymmetric, yes. Yeah, without a doubt. Asymmetric, E, or the new version, 989. That's and it's not like everybody uses the BLF range because there's only one transmitter manufacturer really in the world, apart from a small company in Japan. But it's the old Philips manufacturer that changed its name to Ampelon and NXP, but it's still the same manufacturer. They have a place in Rhode Island and a factory in Austin, Texas. Most of them are made in the Philippines. The actual transistors are made in the Philippines.
So if I have an older transmitter and it's got enough headroom in it, and I may have that, I'm not sure. got enough headroom, I could do 3.0.
Yeah, absolutely.
Just be less efficient.
Be much less efficient, yes. The power bills will be higher. But yeah, if you've got plenty of headroom, then there's no problem. Is it a solid state or an IoT?
Yeah, it's a linear system,
Okay.
fairly modern. I mean, it's 7 or 8 years old. But
So that would have the original, let's see if this says BLF 888E, you have the BLF 888A, the one. It's a non-Doherty transistor. It's non-Doherty, but it would work, just won't work very efficiently. So that's the transmitters. STL, there could be a good chance that you need an STL because we're now working on all IP. The input to your transmitter will be IP. So you'll have to have some way of getting the signal to the site if you use your existing STL and then changing it into an IP format. So most people will have to change it. Transmission line, and most of the time that won't need to be changed. People, when you design transmission line, you typically design it with a large overhead. If it wasn't designed with a large overhead, then you have a problem. But most of the time, you should be good. Unless you're significantly increasing the power. Now, a lot of people have moved to circular polarization. That means they're not just putting the signal out in the horizontal plane, but they're also putting some of the power in the vertical plane. That means you're doubling the power or increasing the power. And if you increase the power, then the transmission line increases and the antenna increases, and obviously that may need a new transmission line and may need a new antenna. And the same goes for the antenna. If you go for vertical polarization, maybe the ideal coverage, as my friends at Dielectric have told me a few times, is between 25 and 30% in the vertical. It is usually sufficient to meet the requirements. That means it penetrates houses a lot easier. It works on cell phones because you're moving a cell phone in many different angles, or mobile devices. So vertical polarization, 25 to 30% is probably a good idea. But that 25 to 30% has to come from somewhere. So you either reduce the power of your horizontal signal, which is probably not a good idea, or you need a lot more power in your transmitter. So that means, again, not just do you have the 2 dBs for ATSC3, but you have that another 33%, another couple of dBs there. So you're talking about more than double the power of the transmitter. So if you're 10 kilowatt today, you'd be looking at a 25 kilowatt in the future for the same kind of coverage. And I just covered that. Okay, looking at the entire system, I put this picture together. What are you going to need to change to move to ATSC3? Well, logically, if you want to get information in 4K, you're going to need 4K cameras. And if you get 4K cameras, you're going to need 4K ultra-high definition production system. Mostly, I've color-coded these, so green means it doesn't change, red means it's going to change and you need a new one, and yellow means you may have to change, depends. So like the master control, you might be able to just put interfaces on either side, and that should be sufficient. You're definitely going to need an ATSC3 encoder. They don't call them multiplex. You need an ATSC3 encoder, of course, because it's a different kind of encoding. It's what's called HVEC, high efficiency video encoding system, or H.265. You're going to need a new multiplexer, which is known as a gateway, and a new kind of electronic service guide, like PSIP. Obviously, you're going to need a new exciter at the transmitter site. The transmitter's most likely okay. The bandpass filter is mostly okay. And then from the receiver point of view, all of that changes as well. From what's called a home gateway, that's basically a receiver that can pick up ATSC1 and ATSC3 and retransmit them through a Wi-Fi device, like a router. And then that can be picked up in your house, on your TV, on your smartphone, on your smart TV, on your tablet. If anybody wants to see one of these, by the way, we have one in our booth. They are currently available. It's called a home gateway. It's designed by one of our partners from Korea, because they implemented ATSC3 in Korea. They are available for sale now. And so you could go live ATSC3 if you really wanted to, and you could have people watching your station as well. All right, Before I jump, yes, sir.
Is that a DS broadcast gateway that you're using, or the one you just referred
Well, it's under our name, but the original company is a company called Digicap. And Digicap, we're the exclusive sales stream of Digicap. They provided all the ATSC3 receivers and gateways in Korea. They also are the designers and developers of the actual encryption system in Korea that's used. So if you want to see one, as I said, we've got one on our desk out there. Broadcast Electronics. Yes, sir.
If you put up the previous slide,
Mm-hmm.
that pink, almost centered square at the bottom.
This one?
Yes, should there be a comma after encoder?
Yes.
And a comma after multiplexer?
No.
Those things aren't all in one, they're three different things, aren't they?
And not from our box, they're not, no. I provide this. I can sell you that, and it's all in one server. And in fact, it's not even in, I can even sell it to you in no boxes. I can do everything via the cloud. So, yep, that's what we're offering. Now I enter into the sales pitch here, put my salesman hat on. We can sell you this as a complete package. You can provide the servers, so that box that's shown could be your box. And then we'll just put the software on there. And inside there is the encoding, the multiplexing, it's called packetizing, the PLP generation, the scheduler, and an electronic program guide, and even the emergency alert systems. And that,
So you realize that all three gotta be done, so you put them in one box.
yes, we did. And we are, because this, to give you some numbers here, you can buy these boxes all separately. You can go out and buy an encoder from one company, a gateway from another, an EPG from a third company, and you add all those up together today, and it's about $120,000. Those three items, depending on how many channels you do HD. So we are offering this, if anybody's interested. And as I said, this wasn't a sales presentation. It wasn't supposed to be a pitch here, but we offer them over the cloud, so you don't actually pay anything. You just pay you pay a monthly fee, and the cloud services, but you pay a monthly fee to run that. So encoding, everything you need in that, as you said, one box or multiple boxes.
But you will sell the box.
I can sell you, yes, it's a server. And as I said, they're expensive. However, just as a side note, and if anybody is interested, if you wanted to go ATSC3, but you didn't want to do all the whiz-bang effects, but you just wanted to go ATSC3, maybe check coverage, maybe check, how it works, get a good feel of it. We do something actually inside our exciter that will take an ATSC1 signal and turn it into ATSC3. And it will actually transmit real ATSC3 in an OFDM format. You can pick it up with an ATSC3 receiver, and you can watch your ATSC1 programs. So if you have 4 programs today, .1, .3, .2, and so forth, you would be able to still pick those 4 programs up in ATSC3, but you won't be able to get any of the features of ATSC3. And you can do that for about $8,000. So there's a quick way of going ATSC3, checking coverage, testing it out for a very low investment. You don't have to buy, it's not the strongest laser I've ever seen. You don't have to buy cameras, you don't have to buy production, you don't have to buy any of this stuff. It's basically a little piece of this is either in there or you can leave it there, either way. So, yes, sir.
Okay.
What's your name again? I didn't catch it.
Who knows? Yeah, I'm Dave Bacon
It's
from
David, by the way.
COACB. Okay. Now, we broadcast 6 streams,
Yeah.
okay? So what would we have to do to replicate those 6 streams in ATSC3? What, from that,
So we can provide you a little box that sits here or it sits there that will take your ATSC 1 stream and it will turn it into an ATSC 3 stream. Now, so here's something that you might think about. Everybody's thinking, well, what's the point of that? You know, it's the same as ATSC 1, the same video and so forth, but it's not. Don't forget, ATSC 1 is a single carrier system, and to be very frank, it's horrible trying to pick it up. You have to have an outside antenna. You have to have an antenna. You shouldn't walk near the antenna. Do not touch the antenna. Anywhere go near the antenna and you lose. ATSC 3 is not like that. It has the same reception capabilities as your phone, because it's OFDM, and a lot smaller signal. So with a small antenna this big in somebody's living room, they will have perfect reception of your ATSC 1 signal, which they're not doing now. So maybe a station could improve another station's coverage and quality and indoor reception just by installing an ATSC 1 to ATSC 3 adapter on a temporary basis. The FCC will allow low power stations to do that without any change in license. I do not believe you're allowed to do, yes you are allowed to do that with Class A and full service, because you're carrying a full service signal. So anybody could do that. It's a way of jumping into the future without very much of an cost. Of course, you'll need to have an ATSC 3 exciter as well, but they're not bad. That is the end of the presentation. Did I go over?
No, we're okay.
Okay, good. And there's my summary there. And the last thing, we really do have a bright future. That's the key. Yeah.
thank you very much.
You're welcome.